this module, we will be discussing several modulation techniques, some additional modulation techniques actually, concentrating mainly on quadrature phase shift keying and M-Array PSK. There are in fact lot of other modulation techniques that one can talk about, but due to the limited scope of our course, we will stop with QPSK and a general discussion of M-Array PSK. For some interesting modulation techniques, we will have to wait for the end of the course, at which point we will again come back to the transmitters and then talk about some newer modulation techniques. So, for now in this module we will simply concentrate on QPSK and M-Array PSK. I will talk about the formulation as well as the optical implementation for these two transmitters. Okay. Compared to a binary phase shift keying, in which you can write down the constellation point as consisting of 2 points which are separated by a certain distance. So, let us say this first point is located at square root of Es, the second point here is located at minus square root of Es. Remember, this is the I and this is the Q components, right. I mean, this is the signal space that we are considering, this is the complex signal space that we are considering, and these 2 points which are marked by the cross marks correspond to symbols 0 and 1. I could interchange the symbols from 1 to 0 in this way as well, depending on what I am going to assume. So, this is basically left to the discretion of the user, whether you want to associate plus square root Es to the bit 0 or minus square root Es to bit 1. In this case of binary phase shift keying, the phase of the carrier is keyed or is changed between 0 and pi, right. So, I have, for let us say if I take this as the mapping that I am considering, this as the mapping with 0 and 1, 0 mapped to phase 0 and 1 mapped to 180 degrees, then if I have a sequence that I need to transmit, let us say 0, 1, 1 and 0, right. The corresponding waveforms that I would like to transmit here would be square root Es cos 2 pi FCT. Note that there is no phase change here. In order to normalize these energies, because when you take the energy of this one, the energy would have a term corresponding to the symbol period. So, in order to normalize those values, we can divide this by square root of Ts. We can also multiply this one by 2, so that when I take the energy of this waveform, the energy will be 2 Es by Ts square root whole square multiplied by Ts by 2, right. So, that when you expand this square root, you will see that the energy is given by Es. Es stands for the symbol energy, in which case this is also the bit energy, right. So, in this case the bit energy is equal to the symbol energy. So, because of this reason we will use square root of Es by 2s as our amplitude of the carrier. Okay. So, in order to transmit 1, right after this bit or the symbol boundary is ended, in this case bit boundary is equal to the symbol boundary, because this is a binary phase shift keying. So, in order to transmit a 1, for the next t duration, Ts duration, I should transmit minus square root of 2 Es divided by Ts cos 2 pi FCT. Again, when this ends, I should transmit minus square root of Es by Ts cos 2 pi FCT. Here I should switch or change the phase from 180 degree to 0 degrees and then transmit. So, if you were to look at it as a function of time, this is how you would see this. So, these are my boundaries. This is highly exaggerated, as I have told you in the last module as well. The carrier is very high frequency, but we will write some few cycles in order to show you how the phase change is happening at the boundaries. So, this is Ts, this is 2 Ts, Ts stands for the symbol period. In this particular case, it is also equal to the bit period, because Ts is equal to Tb. So, to transmit square root 2 Es by Ts cos 2 pi FCT, I have to transmit this cosine waveform. So, please forgive me if my cosine waveforms are not very nicely looking like a cosine waveform. It is kind of hard to draw it on this part, and let us say my cosine waveform, which has to have an integral number of multiples here, must end at this point, right. I need to satisfy, as I told you, Fc into Ts must be equal to n, where n is any integer, it has to have an integral number of cycles. So, this is my cosine signal representing the bit 0 or the symbol 0. Next what I have to transmit is minus square root of 2 E s by T s cos. Well, this amplitude is square root of 2 E s by T s, whereas how would the amplitude, how would the signal minus square root 2 E s by T s into cos 2 pi f c t would change, or how would we draw it? That needs to be transmitted like this, right. So, I need to transmit in this way. So, hopefully I am trying to convey here, and this is looking okay. Next I have to transmit again a 180 degrees. So, I have to switch over and then transmit a 180 degrees, right, and then I have to transmit a 0 degrees. So, it would actually be something like this. Okay. So, if you notice here, what has happened here is, if you notice at these points there is a change in the phase. So, at this point the phase goes from 180 degree to 0 degree. So, this sudden transition of this phase, from going to 0 to 180 degrees is important, because these transitions represent the signal transitions or the phase transitions, right, corresponding to what sequence you are transmitting. And to implement this using an optical transmitter is quite simple. To implement this one, all I need to use is a laser diode. I need to have some signal source. So, I use a laser diode. The output of the laser diode can be pulse shaped. So, I use a pulse shaping MZM. So, to the pulse shaper I might supply an RF signal, so that I get a 33%, 67% or 50% output optical pulse shapes, right. Once I get the optical pulse shapes, I just have to use a phase modulator. Whatever the bit sequence that I am getting here, Bn, which can be a sequence of 0, 1, right. So, it can only take on the values of 0 and 1. So, this particular sequence that I am transmitting comes out as Bn, and this needs to be given as input to the phase modulator. If you wish, you can include an electrical block here which will do an electrical pulse shaping. So, let us call this as some g of t, right, and then you have an optical pulse shape which is coming out as say p of t. Maybe I have switched p of t and g of t notations from the earlier module to this module. It is simply important to note that optical pulses are going in as input to the phase modulator, and there is an electrical pulse shaper which will take this b of n. It will also multiply it by a certain constant, right. You need to multiply this one by square root of 2 E s by T s, or you can adjust the amplitude or adjust the power of the laser diode in order to get that power value of 2 E s by T s. Okay. So, this you can either adjust it by the laser diode, or you can adjust it by the bit sequence map multiplication, does not matter whichever way you do. What you get here is the BPSK signal. Okay. Now, with BPSK signal you are able to transmit one bit for one symbol, right. So, it occupies a certain bandwidth. We will come back to the bandwidth calculation in terms of power spectral density after some time, but if you look at the power spectral density, which is having a certain width corresponding to the bandwidth of this particular modulation technique, you will see that for that given bandwidth you are able to transmit one bit for every symbol that you transmit. Now, this transmission of one bit per every symbol for the given bandwidth seems to be kind of wasteful, or in the sense that it is kind of a minimum that you can do. Is there a way to increase the spectral efficiency? That is, can I increase the number of bits per symbol while keeping the same bandwidth? For example, in optical communication systems, you have 100 gigahertz grid, 50 gigahertz grid, sometimes you also have a 25 gigahertz grid. What this grid means is that from channel to channel you have about 100 gigahertz of separation, that is, each channel has a sort of bandwidth of 100 gigahertz. This is the two-sided bandwidth that we are talking about. So, in that 50 gigahertz, for example, if you assume, so if you assume a 50 gigahertz bandwidth, right. So, in that 50 gigahertz bandwidth, if you were to use BPSK, you will be sending 1 bit per symbol, okay. And if I want to increase the number of bits per symbol while keeping the same 50 gigahertz bandwidth, I cannot use BPSK. I have to use a different mechanism in which I am able to send 2 bits per symbol. Okay. Such modulation or such mechanism by which I am increasing the spectral efficiency, that is how many number of bits per symbol for a given bandwidth, that is the definition of spectral efficiency. So, how can I increase spectral efficiency? By going to what is called as higher order modulation techniques. Higher order modulation techniques means that you will be utilizing the phase and the amplitude and combining them in certain ways, so as to increase the number of bits per symbol. Okay. One simple solution to increase the spectral efficiency is to use what is called as quaternary phase shift keying. Quaternary stands for 4, so your phase goes through 4 different values. Okay. There are various ways in which you can arrange them, and we will of course look at the standard QPSK format. So, standard QPSK format is given by the constellation point that would look like this. The constellation values are pi by 4, then you have 3 pi by 4. So, this is pi by 4, this is 3 pi by 4, then you get, I suppose, 5 pi by 4, and then finally you get a minus pi by 4, because 7 pi by 4 is minus pi by 4. So, if you look at the I and Q axis for this, and if you say that this angle is pi by 4, as well as this point here you have chosen to be at Es by root 2 plus j Es by root 2. Okay. So, this would be the amplitude of the signal that I have chosen. That okay? Or rather I should choose square root of Es by 2. If I take Es is equal to 1, some sort of a normalization that I can do, then these points, the points corresponding to pi by 4 angle is located at 1 by root 2 plus j 1 by root 2, and 3 pi by 4 is located at minus 1 by root 2 plus j 1 by root 2, and so on. I will leave the other two as exercises for you to complete the phase to amplitude or phase to complex amplitude mapping. However, there is one thing that we have not yet done. Remember, in the BPSK modulation that we had taken, we had talked about, first we had a bit or a symbol, or rather if you go back to the constellation, you had the constellation points, and these constellation points, which are simply some numbers in the IQ space, they had to be mapped into the corresponding symbols. BPSK symbols is equal to bit. In this particular case, you have 4 such constellation points, and you can actually map these 4 constellation points to 2 bits per constellation point. Correct. So, I can map this as 0 0, 0 1, 1 0 and 1 1. Or if I go to what is called as the gray coded modulation, I can map this to 0 0, 0 1. Notice here that I will make it as 1 1 and then cause this to 1 0. This blue one which I have written is the gray coded constellation. The other one which I have written in the orange color is the simple binary mapping. This one is the one which I have written in the orange is binary, here in the blue is gray. So, this is the gray coded model and this gray coded modulation, and this is the binary, straight binary encoding formulation, right. So, what you have done is you had these bits with you, and those bits or the group of bits which form a symbol. So, you had symbol or bits, bits or symbol, both of them are equivalent, and that has been mapped onto the phase. Phase has been given by a certain value of the signal that is being carried out, right. So, what you have done is to take the bits, group them into symbols, and then map these symbols onto corresponding phase of the carrier. So, in general, for a QPSK signal you can actually write like this. The expression for this QPSK signal can be written as the ith waveform. Okay, there are 4 waveforms obviously. So, this ith waveform that you are taking is given by square root of 2 Es by Ts. Remember why I am multiplying this one by square root of 2 Es by Ts. Then you have cos of 2 pi Fct, which is the carrier frequency, minus 2I minus 1 into pi by 4, okay, where I goes from 1, 2, 3 and 4. This is not the only way to represent, but this seems to be the simplest way for me to represent this signal. So, if you look at this ith waveform and calculate what is the energy of the ith signal, the energy of the ith signal will be equal to Es. How many waveforms do we have? We have 4 waveforms, each carrying an energy of Es, and what is the average energy carried by each symbol the average energy carried is equal to Es. Okay. So, if you look at the expression for Si of t and invoke the formula cos A minus B, right, cos A minus B is given by cos A cos B plus sin A sin B, and apply that directly to this expression of Si of t, you can write the ith waveform as square root of 2 Es by Ts cos 2I minus 1 into pi by 4 times cos 2 pi Fct minus square root of 2 Es, or rather plus square root of 2 Es by Ts sin 2I minus 1 pi by 4 sin 2 pi Fct. Is that okay? So, now you can see that you have actually written down Si of t, where I goes from 1, 2, 3 and 4, these are the 4 values. You have written down this as some signal multiplied by cos 2 pi Fct and another signal that is multiplied by sin 2 pi Fct. And if you now denote by phi 1 hat of t this particular waveform, which is cos 2 pi Fct waveform, and with phi hat 2 of t, that is phi 2 hat of t as this waveform 2 square Es by Ts sin 2 pi Fct, you can clearly see that phi 1 of t is orthogonal to phi 2 of t. You can easily prove that because Fc is integral multiple of Ts or 1 by Ts. Because of this, these two are orthogonal to each other, and I can write Si of t as cos 2I minus 1 by 4 into pi multiplied by phi 1 hat of t plus sin 2I minus 1 pi by 4 phi 2 hat of t. Okay. So, if you now go to the signal space representation and then call this as the phi 1 axis and call this as the phi 2 axis, right, then I can, by changing the value of I, which is say 1, 2, 3 and 4, I can find out what would be the corresponding points on the signal space, right. So, the corresponding points are cos 2 I minus 1 pi by 4 comma sin 2 I minus 1 pi by 4. So, this is the point on the phi 1 phi 2 plane which can represent the different symbols. So, put I equal to 1, you get 2 minus 1 is 1. So, cos pi by 4 and sin pi by 4. So, you get 1 by root 2 and 1 by root 2, whereas if you put I equal to 2, you get, putting I equal to 2, you get cos of 4 minus 1, which is 3 pi by 4. Cos 3 pi by 4 is in the second quadrant. So, this would be minus 1 by root 2, and sin 3 pi by 4 is in the second quadrant. So, it is positive there. So, it is 1 by root 2. You can complete for 3 and 4 obviously, and then you will see that these are nothing but the original constellation points that we had talked about, right. So, these are for I equal to 1, I equal to 2, I equal to 3 and I equal to 4. If you wish, you can use the straight notation or the gray coded. So, with gray coded, this is 0 0 0 1 1 1 and 1 0. Is that okay? 0 0 0 1 1 1 and 1 0. So, this would be I equal to 2. So, this would be minus 1 by root 2 and plus 1 by root 2. You have the gray coded constellation of these 4 points, right. So, this is the standard QPSK format. You can realize this standard QPSK format using optical transmitter in a very simple way. As usual, you have the laser diode, and then you have the pulse shaper in the form of an MZM. To the pulse shaper, we can give an RF signal running at FR by 2, which is the data rate by 2, and choosing the appropriate amplitude and the biasing condition. Then you have your IQ modulator, right. So, you have your IQ modulator, which consists of 2 inputs, I and Q, right. So, you have I and Q, and this is your IQ modulator that we discussed. All you have to do is, whatever the symbol that you are getting, so call this as the symbol sequence or the bit sequence. So, if this is the bit sequence that you are getting, you essentially put a demultiplexer over here, okay. So, you put a demultiplexer, let me rewrite here correctly. So, I put a demultiplexer after the symbol or the bit source, and then extract the I bits and the Q bits. So, I am trying to write it in such a way that I am connecting this I and Q. Okay. So, I have the I bit here and the Q bit connected. So, please note that this is actually a jump connection here, it is not straight connection. So, what is the reasoning behind here? I know that the corresponding points are cos pi ui of t by 2 v pi and cos pi uq of t by 2 v pi. So, this is essentially the transfer function of the I and Q modulator, right. So, these are the 2 points with which it can reach. So, by sending the I signal to this and Q signal here, of course, if you want you can also put in a electrical pulse shaper, right. So, you can put in an electrical pulse shaper which is g of t and also suitably scale up this electrical signal. Okay. You have to scale up this electrical signal in such a way that this is equivalent to cos pi, or rather this one should be equal to cos 2i minus 1 into pi by 4 kind of a situation. Okay. And this one should be sine. So, in order to have this sine, you have to operate this Q modulator by an additional, you have to give an additional phase shift of 90 degrees to this, right. So, that this becomes cos pi ui by 2 v pi of t, cos, or instead of cos it becomes sin pi uq of t by 2 v pi, and then put the biasing conditions in such a way that you get this term as pi by 4, and then you can go through the different values for I and then see that using the IQ modulator you will be able to implement the standard QPSK modulation. Okay. Now, there is another way in which I can implement QPSK signal, and this implementation is widely used in the 40 Gbps optical communication systems. This is called as differential QPSK. Okay. With differential QPSK, what we do here is that instead of encoding the bits into their corresponding symbols and symbols into their corresponding phases, we encode the phase difference. For example, let us consider the simple DBPSK, right. So, if you look at the actual BPSK configuration, you have a 0 here and a 1 here, that is the mapping which I have chosen. So, these are the symbols. If my present bit is 0 and if my next bit happens to be 0, then I am in the same phase, right. So, I do not have to change the phase. So, this can be encoded by giving a 0 phase difference, or by sending out a signal whose phase is 0 radians. If my present bit is 0 and the next bit is 1, there is a transition of 180 degree phase. So, this transition can be represented by sending out a pi shifted carrier signal. Okay. If my present bit is 1 and the next bit is 1, then I am in the same phase situation. So, I represent this one by a 0 phase. So, I represent these transitions by pi. Similarly, I represent this transition by pi. Okay. So, in order to implement a DBPSK modulation, you simply use the same BPSK modulator, except that instead of sending the straight BN sequence, the bit sequence, you then differentially encode them. Okay. You differentially encode them to generate the differentially encoded sequence. The details of this you can see in the exercises that we give out for this particular module. Okay. I do not want to go into the details of that, that is not really important for us, but you can extend the same idea to differential QPSK as well. Remember, in the QPSK you have 4 different phases, right. So, this is pi by 4, you have 3 pi by 4 and then 5 pi by 4 and then 7 pi by 4, or which is equivalent of minus pi by 4, correct. So, what possible transitions can I have? There will be 0 phase transition, that is the present group of symbols is 0 0 or the bits is 0 0, the next symbol is also 0 0. So, I have represented that by, I can represent that by sending out a 0 bit. This transition from pi by 4 to 3 pi by 4 is 90 degree transition, right. So, I can represent this transition by sending out a pi by 2 shifted cosine signal. This transition from 5 pi by 4 represents a pi transition, and similarly pi by 4 to minus pi by 4 would represent a minus pi by 2 transition, right. So, if you look at what the differential encoding that I need to do, I have 4 different transition points, which is 0 phase difference, pi by 2 phase difference, pi phase difference, and finally I have minus pi by 2 phase difference, right. So, I have these 4 possible combinations, and if this represents a straight binary coding 0 0 0 1 1 0 and 1 1, the differential coded bits can also be represented as 0 0 0 1 1 0 and 1 1. But please note that this 0 0 in the straight binary format or the standard QPSK format denotes different phase, whereas this 0 0 here indicates the same phase difference. One thing for differential BPSK or for differential QPSK formats is that you need to have an initial dummy symbol. Okay. So, you need to have an initial dummy symbol. This does not really matter because you are only looking at phase difference, but this dummy symbol should be known for both transmitter as well as the receiver. So, for the BPSK case, let us say the dummy symbol is 0. So, if my first bit is 0, the previous bit was also, or the dummy bit is 0. So, in the next case I can write this as 0 phase, right. I can transmit that corresponding slot as 0 phase shifted signal. Okay. So, similarly you will have to have a dummy symbol. Let us say the dummy symbol for the differential QPSK signal is 0 0. Okay. So, the way to implement this one would be the same as we have discussed. One final modulation that we are going to discuss here is called as M-ARRI PSK. The idea behind this is very simple. You go to the constellation diagram over here. So, it could be phi 1 and phi 2 space, or equivalently I and Q space, that is phi 1 and phi 2 are the real space, I and Q is the one single complex symbol space. Okay. So, phi 1 phi 2 is the real 2D space, whereas if I use I and Q, that would be one complex space, right. So, this gives me complex symbol, this gives me real symbols. These are just the way of representing them. So, for an M-ARRI PSK, consider the simplest case of m equal to 8. What different possible phases that you have are 0, pi by 4, pi by 2, this one which is 3 pi by 4, pi, this one pi by 2 and minus pi by 4. Sorry, they are supposed to be arranged in a nice circle, but I could not draw a circle properly. So, I have actually 8 different phases, right, and each of these would be representing a group of 3 symbols. So, this is 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, this is straight binary configuration, 1 0 1, 1 1 0 and 1 1 1. How do I implement this? You have the usual culprits, the laser diode, the pulse shaper, but for representing these phases you can simply use 3 phase modulators. Okay. So, you will use one phase modulator, another phase modulator. This phase modulator will be biased between 0 and pi, that is in order to generate 0 and pi phase shift. This will give you 0 and pi by 2, whereas this one will give you 0 and pi by 4. So, if you use a bit sequence and then put a demultiplexer over here and then send in the MSB bit to the first phase modulator, send the middle bit to this one and then send the LSB bit to the last phase modulator, you can see that the total phase that you will be obtaining will be a linear combination of all these 3, and it will then implement this one. Thank you.